Welcome you all to the lecture series of Digital Electronics KE 039/049. Myself Dr. Kishanu Kundu, and we are in the lecture number 32. In the previous lectures, we were discussing about various type of PLDs, and today we are going to start a new topic, memory and programmable logic part 1. Myself assistant professor from Department of Electronics and Communication Engineering, GL Bajaj Institute of Technology and Management. So, let us proceed. So, today we will start with random access memory, that is RAM. So, first of all it is actually a memory, type of memory. What is this? A memory unit stores binary information in groups of bits called words. 1 byte is equivalent to 8 bits, that we already know from the basics of digital electronics, and 1 word comprises of 2 bytes. The communication between a memory and its environment is achieved through data input and output lines, address selection lines, control lines that specify the direction of transfer. So, here you can see a memory unit, it is having n data input lines, k number of address lines, and there is some read lines from where the data will be read, and write lines, and we are having n number of data output lines. So, here the memory unit is to the power k words, means the number of address lines having the number of words, means whatever the number of address lines are there, 2 to the power that value will be words of the memory unit. So, content of a memory, each word in memory is assigned an identification number called an address starting from 0 to up to the power k minus 1, where k is the number of address line. Already I have told that here k is the number of address lines, so memory can store up to the power k number of words. Okay. So, here we can say that the address will be up to the power k minus 1, this address. Okay. The number of words in the memory with one letter k, this will be some specification of k. So, if we having value of k is equal to 10, then we will be having the memory size like this. If we having value of k is equal to 20, then the memory size will be to the power 20, like this. So, here we have written something that like if 64 k means to the power 16, 2 m means to the power 21, 4 g means to the power 32. Okay. Next, write and read operation. What is write and read operation? Transferring a new word to be stored in the memory is called write, and transferring a stored word out of the memory is called read operation. Okay. So, what are the steps? Apply the binary address of the desired word to the address lines, then apply the data bits that must be stored in the memory to the data input lines, and then activate the write input. Okay. And for read operation, first of all we have to apply the binary address of the desired word to the address lines, and then we have to activate the read input. Okay. Next, two basic types of RAM. There are two basic types, first one is dynamic RAM and second one is static RAM. What are they? Dynamic RAM losses stored information in a very short time for millisecond, even when power supply is on. DRAM is little bit cheaper. Okay. And static RAM, it will be permanent. Then type of ROMs. ROM, already we have known from the previous slide that there are two type of memory, RAM and ROM. So, already we have discussed RAM. So, now we are going to start ROM. What are the ROM? ROM means read only memory. It is non volatile, means the information stored in it is not lost even if the power supply goes off. It is used for the permanent storage of the information. It also possesses random access property. Information cannot be written into a ROM by the user or programmers. In other words, the content of ROMs are decided by the manufacturers. Okay. There are different types of ROM. There are PROM, EPROM. What is PROM? It is a programmable ROM. its contents are decided by the user. The user can store permanent programs, data, etc. in a PROM. The data is fed into it using a PROM programs. Then next, what are EPROMs? An EPROM is an erasable PROM. The stored data in EPROMs can be erased by exposing it to the UV light for about 20 minutes. It is not easy to erase it because the EPROM IC has to be removed from the computer and then exposed to the UV light. The entire data is erased and not selected portions by the user. EPROMs are cheap and reliable. Next EEPROM, electrically erasable PROM. Okay, this is the third type of ROM, that is EEPROM. The chip can be erased and reprogrammed on the board easily byte by byte. It can be erased with a few milliseconds. There is a limit on the number of times the EEPROMs can be reprogrammed, or usually we can reprogram it for 10,000 times. ROM. A ROM is essentially a memory device in which permanent binary information is stored. The binary information must be specified by the designer and is then embedded into unit to form the required interconnection pattern. Once the pattern is established, it stays with the unit even when the power is turned off and on again. As per block diagram, already we have seen, this is the block diagram of ROM. So, as per block diagram, you can see that there are k inputs and n outputs. So, the size of RAM will be to the power k cross n. Okay. So, from the block diagram is called k inputs and n outputs. You can see from the diagram there are k inputs and n outputs. Okay. So, the inputs provide the address for the memory and the outputs gives the data bits of the stored word, which is selected by the address. The number of words in a ROM is determined from the fact that k address inputs lines are needed to specify to the power k number of words. So, you can see from this diagram that ROM does not have data inputs because it does not have a write operation. Suppose we are considering an example of 32 cross 8 ROM. 32 cross 8 ROM means 32 cross 8. We can write this like to the power 5 cross 8 means 5 inputs and 8 outputs, right. The unit consists of 32 words of 8 bits each. There are 5 inputs lines that form the binary numbers from 0 to 31 for the address. Okay. Now, here in figure 2 we have implemented this ROM, this 32 cross 8 ROM using a 5 cross 32 decoder and few OR gates. Okay. Normally we implement ROM using decoder. So, this size of ROM 32 cross 8 ROM we have implemented using this 5 cross 32 decoder and few OR gates. Here we have having 8 OR gates. Okay. So, let us check. The figure shows the internal logic constant of ROM. The 5 inputs are decoded into 32 direct outputs by means of 5 cross 32 decoder. So, here you can see there are 32 lines, 32 output lines, right, 32 output lines are there. Each output of the decoder represent a memory address. The 32 outputs of the decoder are connected to each of the 8 OR gates. You can see that here these are the horizontal lines, all horizontal lines are output lines and there are some vertical lines. So, there are 8 vertical lines and these vertical and horizontal lines are interconnected. These vertical and horizontal lines are interconnected. Okay. The diagram shows the array logic conversion used in complex circuits. Each OR gate must be considered as having 32 inputs. You can see that here each OR gate having 32 inputs, these are 32 lines. So, we have not written all. So, this is actually array logic, we can say up to 3 we have, then from 28 to 31 we have written, but there exist total 32 line exist in this diagram. Okay. So, each OR gate are having, each OR gate must be considered having 32 inputs. Each output of the decoder is connected to the one of the inputs of each OR gate. Since each OR gate has 32 input connections and there are 8 OR gates, the ROM contains 32 cross 8 means 256 internal connections. So, there are total 32 and these are 8, total 32 output lines and 8 OR gates. So, total 32 cross 8, 256, total 256 internal connections are there. So, this diagram again I am telling, this is 2 cross n ROM means 32 cross 8 ROM, and that 32 cross 8 ROM means we can say to the power 5 cross 8 ROM, and that will be implemented using k cross to the power k decoder, means here value of k is 5, value of k is 5. So, here 5 cross 2 to the power 5 means 5 cross 32, like this it is coming, you can get it right, 5 cross 32 and n number of OR gates, here n is 8. So, here 32 cross 8, so this is value of n. So, this value is here n is equal to 8 OR gates. Now, it is clear how we have implemented the 32 cross 8 ROM using 5 cross 32 decoder and 8 number of OR gates. Okay. So, this is actually a tentative truth table of the inputs. What I have done, just like that you can see that here check out this cross, this connections you have just check, means these are the symbols that these OR gates are connected to the this inputs, sorry this output lines, means see A7 is 1, A7 1, then A6 0, I can check for first one only, see A6 7 1, A6 0, A5 1, A4 1, then 0 1 1 and 0, 1 0 1 1 0 1 1 0. So, this you can check 1 0 1 1 0 1 1 0, like that. So, this is for 0. So, we have to 0 1 2, this is up to 31, 0 to 31 we have to check for all connections, these are the tentative truth table, just we have done like this. Okay. So, you can check like on, like for suppose we are going to check for, we are going to check for 2, suppose 2 is for 2 means 2 means 0 0 0 1 0, this is for 2 input, see this is for 2, this one 0 0 0 1 0, this input. So, for that we can check the output here, what are the thing, see A7 1, A6 1, A5 0, this line we have to check, this line, then 0, then 0, then 1 0 1, 1 1 3 times 0 1 0 1, 1 1 3 times 0 1 1 3 times 0 1 0 1, got it. So, like that we have make a tentative truth table. Okay. So, here we can check. So, every 0 listed in the truth table specifies a no connection, every one listed in specifies a path that is obtained by the connection, means wherever we are having this cross means there are we are having 1. So, there is the connection, this is the connection, this is the connection, this is the connection. Okay. So, the 4 zeros in the word are programmed by blowing the fuse links between output 3 and the decoder, and the inputs of the OR gates associated with the outputs A6, A3, A2 and A0. Whatever I have taught you like in this bigger truth table, same thing we have taken a small partly truth table up to A3 we have taken, and for that we have just written this truth table values. Okay. So, the 4 ones like that were marked in the diagram with a cross denote a connection in the place of dot used for the permanent connection in the logic diagram. When the input of the ROM is 00011, 00011 means this one 00011. Okay. So, what for that all the output of the decoder are 0 except the output 3 which is at a logic 1. Okay. So, like that we have to check the full truth table. So, now let us design a ROM. So, here we have a question that implement this F1 and F2 using a ROM. Okay. So, first of all we have to check make a truth table. So, there are 2 inputs A1, A0 and there are 2 outputs F1 and F2. So, 2 inputs, so 4 combination 0 0 0 1 1 0 1 1. So, this is actually in decimal, this is 0 1 2 and 3. So, we are having for F1 the output we are getting for 1 2 and 3. So, this will be for 1 2 and 3 we are giving high output. For F2 this is for 0 and 2. So, for 0 and 2 will be having high output, and for rest one we are having 0. Got it. So, this thing we are going to implement using the ROM. So, ROM already we have got that this idea means if 2 to the power ROM is 2 to the power k cross n. So, ROM size 2 to the power k cross n, this is the ROM, and the decoder, how many decoder and output we need or gate we need, k to the power k cross to the power k decoder, k to the cross k cross to the power k decoder and n OR gate, n OR gate. So, here we are having this to the power k cross n. So, we will be having 2 to the power 2 cross 4, here k value is 0, sorry k value is 1, k is equal to 1 to the power 2, sorry this decoder will be having means k is 2, k value is 2, so we will be having 2 cross to the power 2 means 2 cross 4 decoder and n value is equal to 2 means 2 OR gates. So, we can implement this ROM using 2 cross 4 decoder and 2 OR gates. So, let us check, very simple, we will be having this 2 cross 4 decoder. Why k is 2? Because 2 inputs only, 2 inputs A1 and A0, A1 and A0, and we are having this 4 outputs 0, 1, 2 and 3, 0, 1, 2 and 3, this is for 0, 1, 2 and 3. So, now we will implement this. So, we can draw like that, there are 2 OR gates, this is for F1, this is for F2, this is for F1, one will be giving F1, one will be giving output F1, one will be giving output F2. Okay. So, let us check, F1 is for 1, 2 and 3. So, all will be, we are having some connection, but here we are having connection for only, we are having connection for 1, 2 and 3. So, for 0 we are having no connection, for 0 we are having no connection for F1, again for this 1, 2, 3 this, and we are having for 0 and 2, we are having connection for 0 and 2. So, we are having for 0 and 2. So, rest of all will be having no connection. You can see the gap here, you can see the gap that is not connected. This we can more clearly we can check, this is no connection here and this is no connection. Okay. You can clearly check it out. This is connected, but here this is what were connected, 0 and 2 is connected, 0 and 2, and this is 1, 2 and 3, this 3 connection are. So, this is a ROM, we have implemented this function using a ROM. Okay, clear? Next, now we will discuss about the combinational PLDs. The PROM is a combinational programmable logic device PLD. A combinational PLD is an integrated circuit with programmable gates divided into an AND array and an OR array to provide an AND or sum of the product in implementation. There are 3 major types of combinational PLDs and they differ in the placement of the programmable connection in the AND or array. Here we are having a figure, you can see here, this is the figure, and here we are having 3 types of PLD. So, let us check one by one. The PROM has a fixed AND array constructed as a decoder and programmable OR array. The programmable OR gates implement the Boolean function in sum of min terms. So, the programmable array logic PAL, here you can see programmable array logic PAL, and this is PROM, whatever we have just studied, this is having PROM. So, PROM has a fixed AND array constructed as decoder and programmable OR array. You can check from the diagram, is a fixed AND array and it is working as a decoder, and here we are having a programmable OR array. For PAL, we has a programmable AND array and a fixed OR array. The AND gates are programmed to provide the product terms for the Boolean functions which are logically summed in each of the OR gates. So, this is the diagram for PAL, it is a programmable AND array and fixed OR array. Okay. And next we are having the most flexible PLD is the programmable logic array PLA, where both AND and OR arrays can be programmed. The product terms in the AND array may be shared by any OR gate to provide the required sum of the product implementation. So, here you can check from the diagram that for PLA we are having programmable AND array as well as programmable OR array, right. So, this is the diagram for PLA. A combination PLD is integrated circuit with programmable gates divided into AND array and OR array to provide an AND or sum of the product implementation, already we have discussed in the last diagram. So, for PROM, fixed AND array constructed as a decoder and programmable OR array, PAL programmable AND array and fixed OR array, PLA both AND OR arrays can be programmed. The required paths in a ROM may be programmed in 4 different ways. So, these are the 4 different ways. First one is mask programming, where mask memory fabrication process, read only memory or PROM, blown fuse or fuse intact, then erasable PROM or EPROM placed under a special ultraviolet light for a given period of time will erase the pattern in the ROM. And fourth one, electrically erasable PROM EPROM erased with an electrical signal instead of ultraviolet light. So, these are the 4 required different ways by which we can erase that. So, now last we are having one more question, that is having design a combinational circuit using a ROM. The circuit accepts a 3-bit number and generates a output binary number equal to the square of input number. So, there are 3-bit number, 3-bit number means we are having 0, 1, 2, 3, 4, 5, 6 and 7. 3 inputs mean total 8 combination, and here what they are telling that our output binary number equal to the square of the input number means here 0 square is, this is decimal 0, the 0 square is 0, okay, then 1 square is 1. So, the output is like this. Then next is 2, then 2 decimal is 4. So, we have to implement in the binary form. So, the output will be 000 100. Then for 3 we are having 9. So, 9 will be written in binary form 1001, then 4 square will be 16, then 16 will be written in the binary value, like that 7 square is 49. So, we have written in the binary form 49. If you have any doubt in conversion of decimal to binary, you can check the previous slides of this lecture series. So, there you can easily get concept of number conversion. Okay. So, we have made our truth table and now we have to implement that. So, here we are having 8 cross 4 ROM. How? Means here 3, k value is 3. So, 2 to the power 3 cross 4 means n value is 4, right. So, k value is 3 and n value is 4, right. And so, we are having this 4 values B5, B4, B2, B1, okay, and we are having 3 input lines A2, A1, A0. So, like that we have made a truth table of ROM. Okay. This thing already we have implemented this here. So, we have taken up to this, okay, B5, B4, B3, B2. Okay. So, this thing only we have written that part of the truth table. So, this is actually the, and you can check here that B1 and B0. So, B1 and B0, B1 is all time it will be 0, B1 is all time is 0. So, we have written B1 all time is 0, B1 all time is 0, okay. And for B naught, B naught is same value of A naught. See here A naught is 0, B naught is also 0, A naught is 1, B naught is also 1. So, whatever the values B naught actually same value of A 0. Okay. So, like that we have connected here B naught is connected to the A naught. So, like that we have implemented this full truth table into a ROM, and that ROM size is 8 cross 4. Already we are having to the power 3 means 3 input lines and 4 output lines. Okay. So, and this is the truth table from which we have drawn the diagram. So, these are the reference and